Thank you for coming and for this controversial and thought-provoking talk. And Diatribe against the law of excluded middle. It's about the notion of truth. And you know, there's nothing like truth in this world. There's nothing like justice. There's justice, quote unquote. As you know, with the Supreme Court, justice is very relative. But the same thing is true about truth. And mathematicians believe naively that truth is absolute. But once again, it's an illusion. One thing about truth, I want to take issue with my great guru, Neil Sloan. It's really a minor incident. There was a conjecture in the OIS that I noticed, some amateurs sent me, and noticed it's completely trivial to prove. And then Neil wrote, these conjectures are now true. So he should have written, these conjectures are now proved. But before, it was some polynomial that was checked for 100 years. It was already absolutely true before. So don't confuse the notion of proved and the notion of true. Anyway, the so-called law of excluded middle, also called excluded third, goes back to a great philosopher, Aristotle. And the Greek name, I don't know, but the fancy Latin name is tertium non datum. It means that every statement is either true or false, and this is already been rebuked many 500 years ago. And I'm sure you all heard about the liar's paradox. I am a liar. I always lie. If I always lie, then it is wrong. So this statement, so it's already been debunked by the so-called Sufist, I think, or Parmenides. This statement is false. True or false? Is this, let's call this statement S. This statement is false, true or false. If it's false, it's true. If it's true, it's false. Hence, it's neither. Neither true nor false. So there was the first example. And this cheap trick has been upgraded by somebody that, in my humble opinion, is grossly overrated. His name is Kurt Gödel. And people think that, sorry to interrupt, Patrick, you paying attention?
Yes.
You know, okay.
Kurt Gödel, highly overrated.
Yeah, but don't multitask. Okay.
Okay.
Thank you. I know he's smart, but so that is me. So he did a variation on this. What he did, he concocted a very complicated number theoretic statement. First, he had a dictionary from logic, from mathematics, to plain old number theory. He looked at the notions of probability. First, he gave prime numbers for every axiom, and he did a very, very elaborate concoction of how to translate a dictionary from any logical statement, for example, provable, to number theoretical statements, including some quantifiers. And then he concocted the famous, very complicated, but explicit number theoretical statement that its meta meaning was not this statement is not false, this statement is not provable. And then he meta-proved that this very complicated number theoretical statement is true. How did he prove it? He cheated. He used the law of excluded middle. So it's a proof by contradiction. Case suppose it's false. Suppose that this Gödel sentence is false. If it's false, then it is provable. Then if it's provable, then it is true. So if it's false, and then it is true. Contradiction. And then Gödel very, very incorrectly concluded using the law of excluded middle. Hence, this statement is true. But it's not provable. But this is complete gibberish, a cheap trick. So what he did prove, that most of number theoretical statements are meaningless. Why are they meaningless? Because they use quantifiers. Quantifiers that extend over the so-called infinite set of integers. And that complete gibberish, a complete misunderstanding. So he did some good. But the interpretation of his work was thus a debunking that most of mathematics, most statements are a priori meaningless. It's true that some statements are a posteriori meaningful. For example, the following statement, n plus 1 equals 1 plus n, for every n. A priori is nonsense. For every n, it means you have an infinite collection of integers, and for every of them you can take. It's true for infinite many cases. It's completely false. I mean, not even wrong. It's not even wrong. It's complete garbage. But it can be reinterpreted. For every symbol, use n as a symbol. So I call it, it's true for symbolic case. So I have a new statement. Every statement, of course, some statements, finite statements, the number of people in this room or whatever, is a priori meaningful, but it's about finite sets. But every statement, even this one, is a priori meaningless. But if you can interpret it as for symbolic n, then it is a posteriori meaningful, if you think of it for symbolic n. So what God proved, that many meta proved, that many things are not a posteriori, even a posteriori meaningless. They are a priori meaningless, some of them. For example, the statement that they do not exist two positive integers, x and y, such that x squared equals 2y squared. In other words, that the square root of 2 is irrational. A priori, it's a meaningless statement. If something is irrational, means we have to look at an infinite collection and look and check whether a square root of 2, whether you take for every infinite set, the square root equals exactly 2. So a priori, but you can make it by reduction, by using the symbol x and y, you can put a reduction. If you exist x and y, then you have exist x by y smaller, so you can make it meaningful for the statement. And the statements that are infinitely many, so use the Pell equation also, you can construct a symbolic formula that for symbolic n, a sub n and b sub n, the solution of Pell's equation. So you can make it sense a posteriori. So from now on, don't use the word decidable and undecidable. Decidable means a posteriori meaningful. Undecidable, even a posteriori is meaningless. So this is the new dictionary. Gödel's was very complicated. A much cleaner version of undecidability was done by Alan Turing. And this was also overrated and misunderstood. The halting problem. So Alan Turing said the halting theorem, better theorem, halting problem is undecidable. They do not. So what is a computer program? A computer program in your favorite language is just a text, a finite statement. And using ASCII code or whatever, you can assign it a number. So you make sense. Question, is a program whose number is n, the nth computer program in Java or whatever, does it ever end? Does it not? Some programs obviously never end. In Maple, while n bigger than 1, print n. It obviously doesn't hide. It goes forever. So for some programs, you can look by inspection that it's not. So then they ask, can you write a program that inputs some text and whether it is not? And Turing had a very clever, basically it's a diagonal trick. to prove that it's not possible. So Turing said the Hartig problem is undecidable. But Dr. Z said the Hartig problem is nonsense. It was a stupid question to begin with. Because it's a program that the program had. It means, does there exist an integer n such that it terminates in n or less steps? And this, once again, look at totality of n steps, integer, so it's completely nonsense. So it's a proof a contradiction that such questions are nonsense, and once again, it's overrated. And speaking of Cantor, also it's misunderstood often what he did. He proved that Aleph 0 is less than Aleph. You can make sense of Cantor's proof. You can use it to prove a very deep result in combinatorics. That for every integer n, symbolic integer n, n is less than 2 to the power n. Here's a beautiful proof. The number of sequences of zeros and ones is obviously the combinatorics 2 to the power n. So let's take any n sequences. A11, A12, A1n. So we have a 0, 1 matrix n by n, and so on. AN1, ANN. Then from these n sequences of zeros and 1, you can make up a brand new sequence. Also of zeros and 1s. 1, A1, 1, da da da, 1 minus ANN. And exercise for the listener or reader. This sequence is none of them. So for every n sequences of zeros and ones, you can come up with another one. Hence we have this statement. And then what Cantor generalized it for an infinite matrix, quote unquote. So even this is true. For the symbolic infinite, and for me infinity is only a symbol. The following row, 1, A1, 1, 1, 1, da da, symbolic, the symbol, is not one of them. So this makes sense as a pure symbolic symbol crunching, and a computer can do it. It's not one of them. Does not belong here. But the conclusion was false. The statement Aleph 0 is less than 2 to the power Aleph 0. Yeah, I apologize to Matthew for using this. Matthew said that I should not use the main middle blackboard because I should exclude the middle. Right? So this. So then Cantor, by the way, that to prove you that dealing with infinite sets is mentally very, very unhealthy. Look at all these poor people. Cantor, he was in a mental hospital for many, many years. Gödel, he stabbed himself to death, basically committed suicide. Post committed suicide, and all this other. As a Unabomber, he also did very, very infinite things. So dealing with infinite could be very, very dangerous for your health. So it should be, the Surgeon General should have a warning. Only if you're very, very mentally stable, you should deal it. Luckily, I don't have to deal with this problem. So, Cantor allegedly proves this. Then he asked, can you stick anything in the middle? And there was the famous continuum hypothesis, the Hilbert problem number 1. And then famously, Paul Cohen, one of my greatest heroes, proved that you cannot prove it. The CH, the so-called continuum hypothesis, this statement is undecidable, quote unquote. And then the question arises. It's undecidable, but is it true or is it not true? Paul Cohen, in my favorite quote, so people think that some people call me a crackpot because I don't believe in infinity. But I have some very good allies Paul Cohen is one. He was a finalist. For him, it was only a game in axioms, a beautiful game. So he has this quote: so he believed that everything. So he didn't believe in the actual infinity. Gödel did. Gödel was a so-called Platonist and realist. He believed that infinite sets are out there and real things, like stars and like this table, but not Cohen. For Cohen, it was just a nice game to play, like playing chess. The king of chess is not a real king, it's just a game piece. So for him, my Paul Keshe, he apologized. He has a very little known paper that should be better known, an exposition. He said he doesn't like to make it public. Whenever you have religious debate about whether it exists, the one who wins the argument is not the one who is correct. It's the one who is better at convincing the personality. It's like politics. So it's nothing to do. The winner of an argument in politics and religion is not the one who is right. It's not the one who is a better convincer or is a more bigger bully in intimidating you into believing. So he was very reluctant to argue. But then he said very, very modestly, because he was very polite, that he believes that it's all a finite game, and the only infinity is the only reality we truly comprehend is that of our own experience. So everything else, the infinity is in our mind. So,
no, he doesn't say that the only reality is what's in our experience. He says the only reality we can truly comprehend.
yeah,
Okay?
that's true. The only reality we truly comprehend is that of our own experience. Very good, thank you.
That makes absolutely no statement about what the reality is.
Of course, yeah, it's about yourself. Yeah, thank you. Yes, thank you, correction. Yeah, so according to me, it's not even wrong. It's a stupid question. I mean, interesting question about a game in axiom, but it's meaningless.
That's according to you, not according to Paul.
Yeah, according to me, right. Yeah, he was wrong. Yeah. So, before going on to the final, so it's so it's completely illegal, completely illegit to use the so-called law of the excluded middle for so-called infinite sets. So let me first point out a famous, that in the previous talk I also did, it's also Wikipedia, erroneous, or not erroneous, but illegitimate use of the law of the excluded middle applied to infinite sets. Theorem! Like this. Okay, this theorem is true in fact, but the proof is going to be false. There exist two irrational numbers such that a to the power b is rational. So this theorem is a very deep theorem because Gelfond proved the square root of 2 to the power square root of 2. Sorry, this is irrational. Yeah, so no, never mind. Yeah, I'm not sure.
He should be not rational, right?
Yeah, square root of 2 is also irrational. So,
Yeah, but now you can modify it briefly.
No, so that's a statement, sorry. The get one is not relevant here. So it is proof. Consider the number square root of 2 plus 1 square root of 2. Case 1, case 2. It's a number. With real number, some real number. You can compute many, many decimal digits in a computer. Case 1, square root of 2 to the power square root of 2 is rational. This we know is false, by the way, but because of that font. But never mind, right now is proof. So in this case, we are done. Thanks to the Greeks, we know square root of 2 is irrational. There's a rational, we found. So take A equals square root of 2, and B equals square root of 2. Wieder, case 2, by the laws of the middle, it is rational or it's not. Then take A equals square root of 2 to the power square root of 2, and B equals square root of 2. By assumption, A is irrational in case 2. So, let's find out what A to the power B is. Square root of 2 to the power square root of 2, quantity to the power square root of 2. Using pre-calculus, square root of 2 to the power square root of 2, then square root of 2, square root of 2 by definition of square root of 2, 2, square root of 2 to the power 2 by definition of square root of 2, 2, and 2 equals 2 over 1. So, it's rational. So in either the case, it's one or the other. But of course, this is completely illegit, because the statement blah 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 is rational is once again meaningless, because you have to check infinite many cases. So that's an example in infinite.
Could you tell us what your criterion for meaninglessness?
Yeah, a priori meaningless. Anything that is quantifying over an infinite set. That's meaningless. The other ways, yeah, but that's meaningless. But sometimes it can be made meaningful by treating it as a symbolic thing.
So anything that involves an unbounded quantifier?
Yeah, it's a priori meaningless. But sometimes you can make it meaningful by considering it as symbols. Like a plus b going to square and a equal to b plus b square could be made meaningful, even though it's true for n and a. So
is that an idiosyncratic, peculiar definition of meaningfulness? That
for me, it's not idiosyncratic.
Or is that something that's supposed to be justifiable for some reasons that can be communicated to other people?
For me, it's intuitively obvious. Okay. And you have been brainwashed by all your education, so for you it's strange.
I'm stupid. And
no, you're not stupid. Okay. You're not stupid, you're misguided. God forbid, you're not stupid enough. Some of my best friends believe in infinity. Some of them even smarter than you. Okay. So, but even, and that's the second part of the talk, even in finite cases, then it is completely legit, but it's still often unsatisfying and gives you wrong, paradoxical, uneasy solution. So you should use your common sense. Sometimes using line logic can lead to undesirable things, even in real life. So then we go to my finite case, my favorite use of the law of excluded middle. My favorite game is called Chomp. So let me remind you, in case you don't know it. It is, I think, due to David Gay. So here the game, you have a chocolate bar, a rectangular chocolate bar, n by n, and it has m times n squared. And you want to eat it, and you take turns taking bites. But the rule is, once you pick a corner, you have to take everything below it and to its right. So if you choose this place, you have to eat everything here. So this is one possible first move. Now it's the second player's turn to move. And then he or she can pick here or here or here. For example, here is this. So that's the next position in this game. So exercise for you, the number of positions is m plus n, choose m. The number of possible considerable positions in this game. Because it's like a path going from the origin to m comma n. And you can say that m plus n choose n. So n of them are vertical steps. So that's this. It's also, if you're not hungry, you can only take one piece. That's perfectly okay. But you cannot pass. You have to take at least one piece. If you're completely not hungry, you can put it in your pocket. And no, we have to eat it, sorry. It's very important to let the whole. Or else you get shot. But one problem is, this is poison. If you eat this, you're gonna die. So, what is the right move? So the initial position is this. So, for small balls, it's easy what to do. Let's illustrate it with a small ball. So who wants to play? One of the greatest experts in games is Nathan Fox. So I'll play this guy. Nathan, you want to go first, or you want me to go first?
I'd like to go first, but I have to think about what I want to do.
Okay.
I'm going to take just the bottom right.
Okay.
I think that's good. So,
Now it's my turn.
yes.
So
That's good.
I do this.
I'm going to take just the one on the right on top. Just the one. Good.
Now I go this.
And now I'm going to take the one that doesn't kill.
And I die. So Nathan beats me. So the question is, in the initial position, and go back to the initial position. What is the right move? And it's easy to see by so-called backward induction. This argument goes back to Ceramello, the same Ceramello Frankel and choice. But it's very simple, that in chess, unless it's a stalemate, you either win, one win. So if it's your turn to move, either in a perfect game, either it's a winning move or losing move. Theorem! This is a winning position. There exists a winning move. So it's a beautiful argument that essentially goes to John Nash, Nobel Prize winner, the late John Nash, in a different context in Hex. And David Gale adapted it to this case. So case 1 or case 2? So consider, So theorem, there exists a winning move. So it's always good to insist that you go first.
So no draw.
No, no, no. It's exercise for you. There's no loops, because always make it smaller, and sooner or later you get to the poison.
Okay.
Yeah, there exists a winning move. So once again, like here, consider the minimal move. So proof. And now the proof is legit. I don't have to put a quotation mark. Proof. Consider the minimal move that you least hungry. You only take
But
this.
this theorem doesn't say whether the winning movement is for the one who starts or the other, right?
No, it does.
You don't?
The one who starts has, if
Win.
he's infinitely
One
smart.
who starts wins.
Yeah, if he's smart. If it's with,
No, I know.
or you have a big enough computer. They exist.
Okay.
Yeah, it's easy to see. It's either a winning move or losing move. If everything that he can do, the other opponent has a winning move, then it's a losing
Of
move.
course.
Yeah.
So the one who starts wins.
That's the theorem. It's not obvious.
Okay, no, it's not obvious.
But it's obvious by the same proof. But it's not that obvious. Yeah. It's a beautiful proof. Consider the minimal move. Let's only take this. So, okay, that's you take this. Case 1 and case 2 once again. Case 1 is a winning move. Case 2, it's a losing move. So case 1 and case 2, that's how the law of absolute middle proof goes. It is a winning move to the